a method of what I call solving continuous, what is spelling of continuous relaxation. Okay. So the idea always has been in approximation algorithm to get some sort of lower bound on opt indirectly or directly. So up until now we have used different ways in the course to find these kind of lower bounds, but now we will give slightly more organized way of deriving these lower bounds on our problem. Okay. So one such problem will be okay. So the problem with which we will illustrate this idea and go forward is vertex cover. So input will be GVE, okay, and there is a cost function from V to R greater than or equal to 0, and what is an output? Output is to find a subset C of minimum weight, cost, such that G minus C is independent. Okay. So that is the goal. So notice when cost function assigns cost of V is equal to 1 for all V in V, this is nothing but minimum cardinality vertex cover. Okay. Okay. So what algorithm do we know for this problem? Via my course. Have you seen this problem in this course? Okay. So all of you say that this is a special case of set cover. So what is a special case of set cover? What do you mean by special case of set cover? So what is my universe? Universe is okay. So universe is edges, and what is my family? What is my family? So for a vertex V, so my family is FV, V in V, all the edges incident on V.
Can we model like this if universe is whole vertex set and family is 2 element subset? So if each edge we will create a family.
So what are you getting? Wait. So what are you getting? So if okay, fine. If I model like this, universe is my vertex set, my family is UV, UV is an edge, right? Like no. So like, what does it even mean? What does it even mean? Wait, what does it even mean? When I give a reduction, I must have a notion of, given a solution of the original instance, I can map it to a solution to the reduced instance. Given a solution to the reduced instance, I should be able to map to a solution to the original instance. I don't think I will be able to do it. Okay. But this is a very valid this thing. So, if I apply set cover algorithm, what will I get? Hmm? It is big O of log, which is log n. Hmm? So, if I specialize this for the case CV equal to 1, what does this implies?
Should be m first, but n is also n square.
Right? What does it implies for if I took CV equal to 1? What does greedy set cover algorithm will imply for vertex cover? What are you doing? If I think of running my set cover algorithm on my graph, what does it imply when CV equal to 1? Huh? Pick a vertex of maximum degree. What else it is? Pick a set which is largest. So, that is nothing but a degree, right? Right? Specializing to graphs, this basically corresponds to pick a vertex of max degree, pick a vertex of maximum degree repeatedly unless until, right, E is phi, right, and this also will give you order log n approximation, okay, right. So, this will give you order log n approximation for vertex cover. Now, here is my exercise. So that greedy algorithm is tight. Right? That is, come up with infinite family of graphs where if I run this greedy algorithm, I will get a solution which is log n times opt. So, in that sense, this is done. Okay. So, now we will in this class we will give a factor 2 approximation. I am sure all of you know this, but like that is not the part. And how I am going to give a factor 2 approximation, I will try to write down vertex cover as a mathematical program. Okay. Write vertex cover as a mathematical program. And how am I going to write this as a mathematical program is that we are going to assign a variable xv in 0 1, which basically means that like for every vertex, right, v in vz, to mean what? To mean that xv is selected, xv is not selected. Okay. Okay. So, basically what I mean is that xv equal to 1 implies v is in my cover. Okay. So, basically what I am looking for, I want to minimize the subset of vertices to be picked. So, minimize summation xv, v in v, okay, and let us say suppose I just write this much. What does it mean? If I start with a vertex cover, what happens then? So, setting xv equal to 0 for all v in v is also a valid solution to this. But if the meaning is that if I go and pick up those vertices, like so, then what in the forward, then what will you pick up? You will pick up c equal to phi in the original graph, but that doesn't have to that doesn't even correspond to a vertex cover. So, as it is written, this program is incomplete, right. So, how can we associate a program such that, what is that called? Okay. Okay. So, basically what it means that somehow this is okay, this is an objective is that I want to assign xv to 0 1, so that some minimization happens, but this first cut is not enough, but we also need to encode the fact that these vertices must pick up one vertex from each edge, right? So what happens immediately, right? So what will happen immediately if I do this? Okay. So actually I should have write CV times XV, because every vertex has some cost associated, right? So we should do that. So what is a constraint that we all, for all u comma v in E, xu plus xv is greater than or equal to 1. So the moment I add this constraint, okay, so once I do this, this is what is a vertex covered ILP, is that minimize cost of this xv, v in v, xu plus xv is greater than or equal to 1, and xv is in 0 comma 1 for all uv in edge and for all v in vg. Okay. So this is what I wrote as my LP. Okay. So what can we prove about this LP? So I think we can prove the following lemma about this LP, this linear programming or ILP. What we can so this is my lemma. Let's see if this is correct. For any graph GVE, okay, and any cost CV, okay, on vertices, okay, CV on vertices, the value of, let's say, vertex cover IP, let's call this vertex cover IP, okay. What is this vertex cover IP? The value of vertex cover IP equals opt, okay. Opt, and what is opt? The cost of minimum vertex cover. Okay. So what I am saying to this is that for any graph GV and any cost CV on vertices, the value of vertex cover IP equals opt. So what will we prove for it? Let's prove it. Okay. So how will I prove it? Suppose it is IP, no? That's IP. Let's call it, I should not call it ILP, it is IP. You will see in a minute. It's just an integer program, right? I do not want to, I have not used the word what linear means, so let's leave it for now. Okay. 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 So what's the proof? So if you are given me some optimum solution xv star to my vertex cover IP, what does it mean? Then I am going to set CB equal to, what I am going to set CB equal to? V xv star equal to 1. I claim that C is a vertex cover, right? And that is true because for every edge, for every edge the constraint says at least 1. So at least one of the guy must be equal to 1. Okay. So C is a vertex cover. So what does this imply? Right? So C is a valid vertex cover of G, which implies that opt is less than equal to this cost, right? Summation over V CV times XB star, right? This is definitely true because this is one potential solution. So one potential vertex cover that we found, this is. Now look at the other way around. Look at the other. So this is like in the reverse direction. So this is what we got. Now I start with opt solution, okay. So we are given an optimal vertex cover C star. I am going to set for all V in C star, you set x B star equal to 1 and 0 otherwise, right. It is a 0 otherwise. It is a valid assignment. Why? Because look at any edge, it's a C star is a vertex cover. So at least one of those guys has been assigned 1. So this So, this is a feasible assignment. Okay. This implies that this xv star is a feasible assignment. Okay. What does that implies? What does this imply? So, right, what is its cost? So, this implies that IP is less than equal to opt cost. The value of IP is less than equal to opt, because this is one feasible assignment. Then what does it imply? What does this imply? Opt is less than equal to this, IP is less than equal to this. So, this implies what? Opt. We are done. So, whatever was the opt solution here, right, if you look at the corresponding thing, that forms a feasible of what cost? That cost is exactly equal to opt, right? Right. So, the value of IP is less than equal to opt, right? But now that means that this is equality holds, right? So, what does this tells us? This lemma tells us that, so this is a background lemma that holds whenever you are doing some of these things. Sometimes this could hold with some approximation, which will imply that if you give me a solution, I can only obtain a solution here with respect to some approximation factor, but that is okay. But for now, we will not worry. So, what does this imply? This implies that if I can solve this object, right, then I can solve this. But what does this implies about this vertex over IP? Huh? And any cost function vertices. What do you mean? See, cost is fixed in the beginning, no? I do not understand what is your issue with the proof.
I am saying that the cost is like every vertex gets a cost of 1, right?
No, cost in the beginning, cost was
xv gets 1, cost is given, now weighted vertex cover.
cost is given. Xv is a variable which tells me whether I buy this vertex or not. If I buy this vertex, this is the cost you will get me, right? Xv just tell me whether I buy or I don't buy that vertex. Okay, is that fine? Okay. So, what we have done is basically converted a combinatorial problem into some math program. Okay. So, what kind of general form of math program that we will be working with? Okay. So, the general form of, okay. So, how does a math program happens? So, a math program has some variables x1, x2, xn, okay, right. So, this is like some x, I have n variables, like x is basically this tuple x1 to xn, and we have some objective function f of x that we want to minimize. Sometimes we can also maximize, but let us focus that we want to minimize, and subject to certain constraint, subject to certain constraints. And what are those certain constraints, right? Of the form some g j x is greater than or equal to 0. So, this is the general form of this, okay. And the number of variables n is called dimension. So, whenever you see dimension in math programming, it is basically the number of variables. So, what are we? So, what is this general program? It is like minimize f of x constraint g j of x greater than or equal to 0, right? Right? And for all j in 1 to m, and say, and what is the property? That x is in Rn. Okay. Okay. So, x is a vector in n dimensional, like r to the power n. Okay. So, let us, being at the cost of being pedantic, let us try to see what is this with respect to this. For vertex cover, what are these objects? What is f of x here? Right. So, what is the dimension here in this program? What is the dimension? Number of variables. So, there is a cardinality of v. And what is my f of x? So, this is what our f of x is, right. So, in my language, this is my f of x, okay. And and there are two kinds of constraints. One is this kind of constraint, other is this kind of constraint. So, how many constraints we have? So, these are like constraint on some g j x, right. Like other places it is 0, that is all that it means, okay. Right. So, basically we have a constraint rather than like g u v x is this for each edge, okay. And the second kind of constraints is more interesting, because they are going to capture x v is in 0 1, okay. But how do I write like this? Right. This is how any math program should look like. Then they should be like this, but that is not what it is. No, what is the meaning of x v belongs to 0 1? So, write it as some function, no, that is write as a function g j x is greater than or equal to 0, otherwise that is not even a constraint in my program. How do I write this? This is much more interesting for me. How do we write it? Right. So, what they have to capture? They have to capture that x v is in 0 1 1. So, do you know a way to capture that? Can you capture that as a math program, like as this kind of constraints? And we are not talking about relaxation. X v is either 0 or x v is 1. Huh? Okay, so that is what he is saying, and that makes completely sense. So, what he is saying that you write g j or z v is equal to, right. So, I can write x v square minus x v is equal to 0. Okay. So, this captures this exactly, right. So, over so this exactly captures this over integer, right. Weight. Okay. Okay. But this is equality. So, right. So, basically it captures two inequality constraints. Okay. So, for every vertex we have two constraints with the function g plus v of x and g minus v of x. Basically, this is greater than or equal to 0 and less than or equal to 0. So, g plus of x is basically exactly this, okay. And what will be g minus of x? It will be x v minus x v square. Is that fine? Okay. So, this is what it. Look, this is what this means, that a is greater than or equal to 0 and a is less than or equal to 0. So, a is greater than or equal to 0, this is the capture, right. Now, I can write this, and this is also greater than or equal to 0. So, what is a less than or equal to 0 is what? This quantity is less, multiply with minus both sides, right, they will change. So, then I can write everything just like this, okay. Okay. So, notice one thing from all this, that because this general math program captures, what is it called? General math programs capture what you call vertex cover in this, of course, they are hard to solve. So, we cannot expect to solve any of these things. Okay. So, in particular, there's a large kind of math program that can be solved in polynomial time is what is called linear program. Okay. So the large part of the program that can be solved is called linear program. So what are linear program? So linear program is when gjx f of x is linear function of x. Then they are called linear program. Okay. Right. So because f of x is linear, so now I can actually, so this function is what? If it is a linear function of x, then this is like some c1 x1, c2 x2, some cn xn, right? So this I can write c transpose x. So this is why you write c. Any linear function can be written as dot product of cost vector and x. So this is why it is minimize c transpose x. Okay. And what else do we have? Okay. So what else we have? And now this is what is called constraint matrix. So it is like A times x is greater than or equal to B, okay, where A is in some m cross n, m constraints, n variables, okay, and what is B? B is in element of R. What dimension vector is this? Column is? It is n cross 1 or 1 cross n. What is this? So B should be an R m because there are m values, right? M constraint for each you have. So this is like a m column, right? That's it. And what is x belongs to this. X is in Rn. Okay. Okay. So if I go back to a vertex covered program, right? If I go back to a vertex covered program, what is, so there are like everything works out perfectly well, but there is one thing which is not well there. What is not well there? What is not well here? These are not linear constraints. So we need to linearize those constraints. Okay, right? So this is why, because that's all that we know how to solve it. If each of this constraint is a linear function of x, then we know how to do this. But here, most of this like one form of constraint is good, other form of constraint is not linear, and hence we can't do this. Okay, so this is what brings us to this idea of what is called continuous relaxation. So now we will do what is called LP relaxation. Okay, so what we will, right? So the idea of this relaxation is to replace what? These hard constraints. Okay, replace with something else which captures the essence of this, and this step is what is called many times linearizing or whatever. Okay, the hard constraints. So in our case, this is like all we have to care is that xb is between 0 and 1. I don't care, right? So I have taken this xv in 0, 1 and this kind of constraint, which if I started to write programs like this, it became a quadratic constraints because the degree of these polynomials are quadratic. But I have linearized them by saying that okay, xv is some value between 0 and 1. Okay, right? So we have relaxed the constraint from xv belonging to 0, 1 by linearizing this. That basically xv is, you can actually say just xv is at least 0. You don't even need at most 1, because for minimization, why do you need at most 1? So like actually you can forget this constraint also, right? Because if I'm trying to minimize, why should I take any xv more than 1? Because even if I put this to 1, I'm perfectly happy. I will still satisfy the constraints. Look at all the constraints where this guy is satisfied with 1 plus epsilon. If I make it to 1, still so that is not a minimization function. Okay. So now what is my LP? My LP becomes minimize summation CV xv, okay, v in v, right? xu plus xv is greater than or equal to 1 for all uv in E, and now xu is greater than or equal to 0 for u in v. So that's it, right? That's it. You understand why there's no point putting that constraint that it is between 0 and 1? Imagine yourself that you have a tuple where xu is like, say, 1.1 plus some epsilon, some vertex. Even if you take this and make it 1, you can see that every constraint is satisfied, because look at left hand side. All you care about are xu plus xb is at least 1. So look at all the constraint where xb is. Even if it is 1, it is satisfied, no? So, but I have reduced the cost. So if I'm trying to minimize this putting that it is at most 1 is redundant. Okay, but like if you want, you can put it. Okay, so what we know, I'm not going to teach you how to solve this program. I mean, okay, that's not. But now you understand that if I can solve this program, so I can solve this program. Okay. Okay. So this is a lemma. What is a good property of this? What is a good property of this minimization? So this is a lemma, theorem, whatever you want to say, you can prove, is that LP provides us, the value of this vertex cover LP, VC LP, provides a polynomial time computable lower bound on opt. Right? Because why? Because anything which is feasible here is feasible here, right? And that's why. So, but imagine that I'm minimizing this set of objects over a large set of objects, right? And everything which is in here is also contained here, right? So I'm minimizing this over this big set, and that is only minimizing over this red set, right? And if red set is contained inside blue set, then the minimum can only be smaller than just minimizing over this set. So there is no more idea, and this is why we can say LP is less than or equal to opt. So LP is less than or equal to, say, opt IP, right? And this is not like, this idea is nothing to do with vertex cover. This statement would be true about any two boxes that you can draw, where one box is contained inside other. If you are going to minimize, right, then over this minimum will only be smaller. If you are maximizing, the maximization can only be larger. Okay. So what we know is that the value of VCLP provides polynomial time computable lower bound on opt IP. Okay, I will just use opt for this thing. Okay, so it's a good exercise for people who don't have done. Exercise, okay. Formulate VCLP, formulate vertex cover as this program, right? It means what I'm saying, write your C transpose, write your A, write your B, blah, blah, blah. Let's see what they are, just to get used to it, okay? And like, you should write down this matrices for a small graph just to get a feeling for what it is, how it is, if you have never not seen it before. Now, we got a solution to this LP. Okay. So what is rounding, which is so much in every this thing, is basically I have got a solution from here. Can I go to a solution here? Right? That is exactly what is called rounding. Okay. So what is this? You are given some x star to LP, and I want to go to some y star to ILP, right, with the help of x star, right. So with the help of x star. Okay. And this is what is called rounding. Taking help of x star to getting a solution to y star is like rounding, right. And I mean, it is bit more okay. And so how do you analyze? So how do you analyze this rounding? You basically analyze this rounding by understanding x star and y star. So one thing we definitely know, right, that y star is less than equal to greater than equal to x star, because x star is an LP solution and y star is an ILP solution, independent of whatever solution I get, right, that cannot be, right, you understand, any solution that I get of ILP here with the help of x star, or for that matter any, I know that is less than equal, greater than equal to. But the question is, right, can I say that, hey, y star is some alpha times x star? If I can say this, then I know this is a lower bound. If I can say this, what does this imply? Now notice, then this will imply this is less than equal to alpha times what? What can I say? X star is less than equal to what? Opt. So I have been able to come up with a solution y star which is alpha times opt. Then what is the meaning of this? Then this is alpha factor approximation. Is it fine? So this rounding is all about coming up with an x star, taking the help of x star to get some y star, and then trying to, I already know that y star is greater than equal to x star because of this. Now if I can show that not only this is actually less than equal to alpha times x star, then I am done, because this implies alpha times opt, and I am very happy. Okay. Okay. For vertex cover, this rounding is very easy. So let us do this vertex cover rounding. Okay, so what is the procedure vertex cover rounding takes? Right? It will take a graph G, right? Cost function C. Okay. And now what will I do? I solve vertex cover LP to obtain, say, xv in 0, 1 for all v in v, right? So this I can solve in polytime. And what is my C? I will set xv, or rather v in v, xv is greater than equal to half. Okay. Return C. So this is what my rounding is, right? What did I do? So you gave me a solution x star. I have got a set C which is v in v, xv is greater than equal to half. So suppose this is like, imagine that I have v1, v2, vn, right? These are vertices, and xv is something, xv like xv1, v2, xvn is my. So what I do, I look at the value of xv1. If it is less than half, I put it 0. If it is greater than half, equal to half, I make it 1, and that's it. That's all that I did, right? So that is all my algorithm did. Okay. So first of all, question number 1, right? Why is C a vertex cover? So first let's prove that, right? Why is C a vertex cover? Like, why is this even a feasible ILP? So I did y star should be a solution to ILP. So that's the first thing. So which means that why the set of vertices which I chose is a vertex cover, right? It means if it is a vertex cover, it will satisfy all these inequality. Okay. So now look at any edge. Look at any edge uv in EG. What is this? xu plus xv is at least 1. So by pigeonhole principle, there exists there exists w in u comma v such that xw is at least half. So that's it, we are done. So now this is a vertex cover. So this is definitely y star to ILP. So this whatever this solution that I made, right, which I called, maybe the best thing is to call this x, and let's call this x star. Okay. Okay. So given this x, I made this x star, right? So this x star is definitely a feasible solution to my ILP. Okay. So that's perfectly great. But now, how does this x star and x relate to each other is not clear to us. Okay. 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 Let's try to understand. I have to understand this, right? Let's look at V in C, right? Look at some V in C, and let's look at xv star, right? What can I write it this as in terms of xv? What can I say? Huh? Is this right? Because when did I make him 1? When xv was at least half, right? So 1, like we made it 1 when the corresponding vertex was this. Then I made this 1, which implies that the value of xv star is at most 2 times the value of xv. Okay. Which is less than equal to 2 times V in C xv, which is less than equal to 2 times V in V xv, which is 2 times LP. I'm done. Right? So this is how I have been able to relate, right? So it was particularly simple object, right? So in the rounding, what happened? I look at some fractional values, right? If the fractional value was large, if the fractional value was large, I rounded it. What was the notion of large? So basically, look, these guys had some value, but they become 0, so they don't contribute. Only people who are contributing, they were contributing half before, now they are contributing 1. So they cannot be more than 2 times. So individually, I can say, what is the value of xv? So basically, think of this way, right? xv star is at least half, right, which is less than equal to xv, which is equal to 1. So now automatically you will get relation from here, right? So this, what we know, this is what I know. So this implies that xv star, no, opposite, okay. This, which is less than equal to xv star, which is equal to 1, right? So what is, I can write about xv star. Is this correct? xv is at least half, which is less than equal to xv star, which is equal to 1. Huh? Yeah, xv is at least half, no? So, what does this imply? If because of this relationship, right? So, this is what we have, right, and this is equal to 1. So, what is this implies? This implies that this is less than equal to, this is 1, right? This I can write is equal to 2 times half, right, because this is 1, right, and which is less than equal to 2 times x v, because half is less than equal to x v. That is it. So, I mean this is much more easier than it is written here. Okay. So, that is what is called a rounding procedure. Now, there is another concept that is used quite a lot is what is called integrality gap. Okay. So, I would like to ask that, is this analysis tight or there is slack, in the sense that, I mean, I have used LP as a lower bound on my solution for ILP, right. Is this like, is this, so I just realized that the ILP which we are able to derive at most 2 times LP, right. But like, is this particular ILP really 2 times away from LP, or it is better? So, what I mean to this is, okay, so this is what is known as integrality gap of the relaxation. So, what is an integrality gap? Okay, so let us call it IG is supremum over all graphs G, right. G is graph, right, and what is this? This is nothing but opt of G divided by LP of this particular graph, right. So, what is the gap between, what is the largest gap between optimum and with the LP solution, right? That is what I mean by integrality gap. Okay. So, what is an integrality gap for vertex cover LP? What is an integrality gap for vertex cover? What did we show? What did we show? What is an integrality gap for vertex cover? Is at most how much? Right? Because for anything we have been able to show that, hey, opt by LPG is at most 2. We have been able to show this. Right? So, for this particular ILP, right, for this particular formulation of my LP and this particular formulation of ILP or whatever it is, integrality gap we have been able to show is factor 2, right, because we use the LP solution and we said, hey, look at this IP, any solution of this, because I made a solution, the best solution can only be less than equal to that. Okay. But is this, the question is, integrality of vertex cover is at most 2. Is IG equal to 2? Is the integrality gap of vertex cover equal to 2? Right? So, can I come up with a family of graph where LP value and opt differs by factor 2? Right? Because this, look at the opt value and look at the LP value, right? They should differ by factor 2. Can you come up with a graph? Okay. Let us look at a complete graph on n vertex graph. Okay. What is the vertex cover of this? N minus 1, and you cannot do anything less than n minus 1. Okay. But now take all half solution for LP. Right? Look at any edge, xu plus xv is at least 1, right? So, what is the value of LP? It's like n by 2, but what is the value of opt? Is n minus 1, right? So, for this, because it is supremum over all graphs, so in particular this graph is also there. So, this is like n minus 1 by roughly n by 2, which is 2, right? So, there is absolutely no hope of improving this particular relaxation. You understand? Right? So, if you think of this way, so this integrity gap goes to 2 as n tends to infinity, right? Very, very close. Is that fine? Okay. Okay. So, what does it imply? This implies that with this particular formulation of LP and ILP, there is absolutely no hope of, if I am going to do this as a lower bound, I cannot show that it is better than, like I cannot show that for this is like 1.9 times LP. This is not possible, because for this graph also that should hold, right? So, this is not possible. Okay, excellent. So, that brings us to the next concept, what is called strengthening the relaxation. Strengthening the relaxation. Okay? Okay. So, I am sure you have seen this lower, Schreiber, what do you call, all those kind of things, right? Serali Adams and all those kind of things. So, these are basically trying to understand these things. So, what I mean, okay. So, now let us still write this by CV, xu plus xv's right. So, this is what, and this is what my LP was, right, and when I made xu is greater than or equal to 0, right, this made to LP. This clique makes this LP cheat ILP with factor 2, okay. You understand? Now, I look at my graph and I can decide that maybe I should write LP differently for this, because it is up to me. Ultimately, I have to solve vertex cover. So, for a different instance, I can write different LP and solve it. It is up to me. I mean, of course, you can write a general LP, but I could, looking at my instance, I decide, okay, for this, let me write this kind of LP and let me solve it and use that to get me a rounded solution, because that is a part of my algorithm. I see my graph, based on the graph, I decide, oh, run this LP, oh, I write something else, I run this LP, and so on and so forth. So, basically what I mean to say, what I would like to do is that I would like to add a valid inequality, okay, that prevents these kind of solution, that prevents these kind of examples. Okay, add a valid inequality that prevents this counterexample, okay, and maybe we will succeed to do better. So, can you think of a inequality? Okay, so what kind of inequality? An inequality, if I want this, so I would like my ILP to satisfy that inequality, but I want my LP to not satisfy this inequality so cheaply. You understand? You understand what I am saying? Because otherwise I am done, otherwise I am not making any progress. You understand what I am saying? The inequality where LP has to work more hard, I mean the kind of things which it was able to do before, it cannot do. Okay. I do not want to say that. All I am saying to you that I want to add, I mean,
because of the way you see inequality, you said that you want the LP, you want to add any quality to the LP,
Okay.
so that the LP has an additional constraint to satisfy, and therefore it is restricted.
No,
And bring
like
it back to
that relaxation also is going to LP, right? It's not that it is this and that is this.
That's why the LP has to satisfy the constraint, and therefore.
So has ILP.
But for the ILP, it is not going to constrain. I mean,
No.
it's
So
the
this.
power of the LP which is making this.
No, Shishma. Like just like
Okay.
look, whatever I'm going to write here, that is same for ILP, right? All whatever so that constraint must be satisfied by ILP. It's great for me.
Yes, but it's the LP solutions that will become more like it will be a subset of the original solution.
Yes, agreed. I understand that, but like that's exactly what we would like to quantify. So this is exactly what I tried to say, right? But these kind of cheating LP solutions cannot be used for those instances. Okay?
So maybe an example.
Of course.
So what type of constraint are you trying to add? Like, are we saying like if we know it's a complete graph,
Yeah, I could do that.
we can add a constraint x1, x2 plus x2 plus x3
Exactly.
equal to
But maybe like, okay, but so it is great that for that kind of instances, I will solve some different LP, so this counter example will not occur. But maybe there are different counter examples. There are different family of graphs where even adding this is not useful for you, right? So can we understand those family of instances? Can we characterize those family of instances? Can we keep adding these things? It's like branching algorithm, right? We find something is tight, okay? I find something is tight and then I try to find ways to get around that by doing something special, right? So I can do it instance by instance also adding this. But what I mean by this, there's something called, okay?
So if I know that my graph has a
N minus 1.
No. So what I understand that we're trying to put in constraint on ILP so that it's not doing far better than the N. Then only this.
Kaban, there's nothing called far better, no Nidhi. Look, it has to have a vertex cover of size n minus 1. This is fixed, right? What do you mean by far better? Look, vertex cover of a click is n minus 1. This is fixed. I cannot change that, right?
Yeah. So what I'm trying to say is that there you are adding a constraint to ILP, right?
I mean, it is added to both, right? ILP, LP, both, right? But it forbids LP to have these kind of solutions.
So this will not be feasible example of feasible graph for that
Hmm.
LP. But then this graph exists.
Yeah, so that's exactly.
What will you do then?
Yeah, you will see, right, what will happen. Huh?
if there is a triangle, you have to select both of them.
That's right. Right? So,
You will handle it differently. This case you will handle it.
so wait, I'm adding this, an extra constraint is greater than or equal to 2 for all UVW that forms a triangle. Okay, so suppose I added this constraint. Every ILP satisfies, every vertex cover satisfies this, right? Every ILP solution satisfies this. But every LP solution previously may not satisfy this. You understand? I cannot put all half solution here because all half is not greater than or equal to 2. So I have avoided all half solutions, which was a like why did LP did well? Because all half could have been the solution here. But now all half if I put, this is not a solution. Okay?
But what will you do for this kind of graph?
Look at this kind of graph, no?
No, it is by adding this constant, you are not allowing it to the feasible solution itself.
What you are not allowing the feasible solution? Find the feasible solution to this LP, no?
Is optimum.
Optimum solution to that LP. Can that optimum solution to LP have all half as a solution?
No.
Then all half is not, n by 2 is not a solution, no?
We have other solution, no?
Its value has increased.
We can put other values except half. That is
look, I solve this LP. Can this LP has all half solution? Then n by 2 is not an optimum, no? So what is the value of that LP? That is not equal to n by 2. But when I wrote my previous LP, if I put all vertices to be equal to half, that LP was satisfied, so that's great. So LP takes n by 2, but my optimum takes n minus 1. But now all half is not a solution to my constraint. That's it. So I have eliminated all half from my possible feasible LP solutions. Okay. So what I mean, okay. So this is what is called valid inequality. So what is a valid inequality? So what is a valid inequality? So basically what? I am adding a constraints to my LP so that certain kind of fractional solutions are eliminated from it, right? So for example, I eliminated all half solutions, but when I add this LP for this, it should always be satisfied by all ILP solutions.
Okay, just one question. So instead of adding an inequality like this, why couldn't we just have said, well, xv, the variables themselves can't take value less than half? That would have also eliminated this.
But that does not, that may not, what that would have allowed?
So xv on relaxation, the LP relaxation, we are saying it will take value from 0 to 1, right? So why
So
can't
I'm writing, no, I have not even written the definition of what valid inequality means.
okay. No, I was saying
No. So first let me write, then,
it was only that.
no. First, then you will understand why I, look, if I did this kind of constraint and ILP goes to hell, then what's the point? If ILP goes to hell, what's the point? If you put all this is strictly greater than half, it means I'm going to always pick all the solution, all the vertices in my solution. So let me first write the definition of valid inequality, no? For an LP relaxation, okay, for an LP relaxation of an IP, of an integer program, okay, LP relaxation of an IP program, a valid inequality is of the form, okay, it is of the form, same thing, like some A transpose X is greater than or equal to some B, okay, such that all integer valued solutions satisfy that. Right? So what happened? So I had first some ILP 1 and say based on that I wrote LP 1, and it is an ILP for the same problem P, okay. So given a problem, I have a set of feasible solution to this ILP, okay. I have some feasible solution, this is blue set, but based on that there is some blue set, right, solution, okay. Now what I mean by constraint, so I added some constraint here, that oh, you need to also satisfy this, you need to also satisfy this constraint. I added, so I add a black constraint which was not before, so now it become LP1 to LP2. Now because these were the feasible solutions before, and now I added a constraint, only less number of objects can satisfy. So but this is called valid constraint if blue set did not change. Like if the blue set did not change, then only I'm going to call this as a valid constraint. Otherwise, there is absolutely no point, right? So what I mean to say is this: why this is called valid constraint is that whatever the feasible solution of ILP was, that does not change, but feasible solution to LP had been restrained. Only then I'm going to call it a valid inequality. Otherwise, I'm not going to call it valid inequality, right? You cannot add here that that, like, of course, when I add a constraint here that the blue solution reduced this for ILP and even this reduced, then this is not a valid solution. I still want to optimize, I still want myself to an option to optimize over all possible feasible ILP solutions. Okay? I can keep adding these things, that's okay, you keep constraining your LP, that's okay, but this should not be constrained, only then I'm going to call it a valid inequality. Okay? Now notice, okay, so suppose I added xu plus xv plus xw is greater than or equal to, so let's write it down. So what we added? So we added xu plus xw is greater than or equal to if UVW forms a triangle, right? Now notice, previously all half was a good, correct solution, right? All half was a good, but now all half will not satisfy this triangle inequality. You are right? But look at any optimum solution that still satisfies this inequality. So here from blue we went to red, but here blue remained intact. So that's a valid inequality that I can add. You understand? Okay. So the integer solutions that is being optimized over that feasible space I have not changed. Only feasible space that I have changed is for LP. Okay. So for example, by doing this, what we have done now? What we have done now, right? What we have done now? If G has triangle, then all half can't be feasible. Is that right? If my graph has triangle, then all half is not a feasible solution, right? Because who will satisfy this? In particular, on Kn, which has so many triangles, this. Now what is the, so now what is the value of LP here? What is the value of LP here? Right? Or like, what is the value here? Now,
There can't be all half, there has to be at least one vertex less than half.
huh?
There has to be at least one vertex less than.
No, I am saying, can you come up with an LP solution here? Which is like feasible, good feasible solution? Huh? Then there's like, the integrity gap is like 1. What's the point? Huh? Yeah, so just set all xv equal to 2/3, right? If I set all xv equal to 2/3, 2/3, 2/3, 2/3, 3 times is 2. So everybody is satisfied, right?
One of the vertices xv's have to be more than 2/3 by pigeon work.
That's okay, that's right. So now I have made every vertex to be equal to 2/3 for now, right? So how much this is? This is going to be, so 2/3 of n is an LP solution. N minus 1 remains the same, but now right? So this is like 3/2. Okay. Okay. So at least by adding this valid inequality, we have gotten rid of this as a counterexample, right? This as a tightness of my integer programming, right? But maybe there are other family of examples where still there is n minus 1, 2. Definitely that cannot be graph that contains a triangle. That will be some sort of triangle free graph. Okay. Okay. So
Does this mean we are like improving the integrity gap?
we are trying to improve the integrity gap. We are hoping to prove that we are okay. So now look what, so in practice what happens is that I look at my instance and I start adding this inequality, valid inequality. Okay. This is what is called method of cutting plane. If you notice, this is what the most cutting plane. Okay. So is that like where you basically do instance based, okay? And this is how you take your LP and you keep adding these constraints and constraint is what is this Sirali, Adams and this and that to make still not lose your optimality and you're constraining your LP or different programming formulation. I should not be using just LP, different programming like quadratic programming, convex programming, this, that.
But ILP feasible space always remains
Same, otherwise if I cannot decide this because maybe the one which you emitted is this. So I mean, if I cannot in polynomial time decide that cannot, if you can, then that's perfectly fine, but if you can't, then forget it. Okay? Okay. So here is a difficult exercise. This is not an easy exercise. Okay, so here's my difficult exercise. Okay, so this is, so now you understand what valid inequality means. This, so there's a very classical paper by, I think this is by, I think what they showed, there's a paper by Bazzi, Fiorini, Pocuta, and Stevenson, that there is no polynomial size LP relaxation to vertex cover problem can have integrality gap of 1.99. You cannot write any polynomial size LP whose integrality gap is like 1.99. Understand? This doesn't even exist. Okay, but that's not what I want you to show. I want you to show the following. It's an exercise. Like there does not exist, like, I mean, is it? Please think about it. All I said on the click it is 1.5. Did I show that on every graph it is 1.5? Then? All I said that clicks are no more reason for the integrality gap, but there could be some other regions for the integrality gap, and by adding those constraints, those regions did not go away. Look, this is one family of examples, right? There could be other family of examples, no, where this integrality gap is 2. Did I analyze that? So we don't know, and you will see here. Prove that the vertex cover LP, 6 cups. Who just tells you how difficult the problem is, basically. Okay, prove that the vertex cover LP with triangle constraint, prove that the integrality gap of vertex cover LP with triangle constraint is at least 1.99. Right? Right. Indeed. Any 2 minus epsilon. Okay. So in particular, find a triangle free graph. Okay, with large vertex cover. Because look, if a graph does not have a triangle, then this constraint is garbage, you know. I mean, if I have a triangle free graph, then you're talking about before and this, but now this is not an example because it's a lots of triangle. So come up with a triangle free graph where you have large vertex cover. Right? It's not easy. Okay, so what did we learn? So we learned, okay. So we learned few things. What is math program? That's one thing. Okay. What are math programs? What is ILP? What is ILP? We also learned definition of rounding, integrality gap. Okay. Is that fine? In particular, find a triangle free graph. Here, indeed, any 2 minus epsilon. This 1.9 has nothing specific. Okay. So now let's do some crash course in linear programs. Okay. 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 So let's do some things which I want to use. Okay. So Okay, so what is this? We have minimize C transpose x, which is nothing but this is the value of LP of x. This is very bad, man. Okay, right. So what was it? That Ax is greater than or equal to B x in Rn. So we are talking only now. We are not no more talking about ILPs. We are only talking about LPs, linear programs. Okay. So this is why x is in Rn, right? A is in Rm cross n, and B is in Rm. Okay. Okay. And you should always know that all these m constraints also include this xi is greater than or equal to 0, and those are also constraints. Never think that they are not constraints. Only xu plus, do you understand that when you write xu plus xv is greater than or equal to 0, sorry 1, and xu is greater than or equal to 0, even this is a constraint. Just only two variables thing is not only, even a single variable thing is also a constraint. Okay? Okay. Where? Is LPX. My God. I thought this is how I is written. Okay. So like for example, if you have a constraint like xi is less than or equal to minus n, then we will always denote it as this. Okay. So this is why we can always, this is the form I will talk about. Okay. So what is the meaning of what is a meaning that some sort of, right? So some look at some AI transpose x is greater than or equal to some bi. What is the meaning of this? Basically, you can think of this as each of them is like a plane. Is like a, so one, those points which is strictly less than bi, and those points which is strictly greater than 0. So bi. So we are only talking about this side, right? So what kind of x we want? Those x which is of this side, not this side. Okay. Now if I look at some other, right, some other guy who will say, okay, no, for me you should look this side, other constraint. So basically what are you looking for, right? So every of this, it basically gives you a half space where my feasible solution lies. So where does x lie? So our x which is feasible solution is in the intersection of these half spaces. Okay. Okay, so this is a fact one. Let's see if we can prove this. If x prime is feasible, right? It satisfies this. Okay, if x and x, then so is theta x plus 1 minus theta times x prime, okay, where theta is between 0 and 1. What is this basically fact 1 tells us? Right? Basically, what does this means? What does the fact 1 tells us? That basically it tells us that intersection is convex set. What is a convex set? If you take 2 points, if you take any 2 points, draw a line between them, it should belong there, right? So basically, if you take convex combination, like all these points on this, like little bit of this, little bit of that, so it's on the straight line. Okay, okay, okay. So like, can we prove? Can you prove this? Okay, so I will not prove this. I'll just leave it for you. Fact 1 to check, right? It's like trivial. It's really trivial. Okay, so okay, but what I would be more interested in is what is called basic feasible solution. Okay. What I would be more interested in is what is called basic feasible solution. So you understand what feasible solutions are. All those x which satisfy this is called feasible solution. And we saw that basically if you look at the set of feasible solution, that is a convex set because of this property. Okay. Okay. By definition, okay, if x is feasible, it satisfies how many inequality? It is satisfies all m inequalities, right? We have m inequalities in this matrix. Okay. Okay. So now notion is some of these inequalities are tight. Okay. Equalities are tight and some are not. So what is the meaning of tight? Means they hold with equality. Okay. So I write Ax is equal to greater than equal to 0, but this is possible that for some rows this is exactly equal to some bi1, bi2, like this object holds with equality. You understand? X is a feasible means all the m inequalities are satisfied, but maybe for some inequality, look at the corresponding row and look at the corresponding, this is holds with equality. You understand? So those will be called tight constraints. Okay. Okay. So let's write down what is T. Basically those rows I in 1 to m such that look at the ai'th constraint, which is ai transpose x is equal to bi. So basically by ai I mean by ai I denote ith row. Okay. Right. So ith row. So if this happens with, okay, and what is the, and rest of the inequality have slack. Okay. What is the meaning of slack? This is actually, this is strictly greater than b. You understand? So because every inequality has to be greater than or equal to b, some holds with equality and some does not hold with equality. Those that do not hold with inequality are called, they have some slack. They have some more gap between left side and the right side. Okay. Let B be a subset of T. Okay. Let B subset of T be the linearly independent rows. Be a collection of linearly independent rows, right? So if I think of this as a matrix, okay, if I think of this as a matrix, like look at this set of rows, like T's are tight, right? Now you basically you find a collection of maximum size linearly independent rows. So basically it's a basis for this, like this B is a basis for, okay. Okay, or like, yeah, be a collection of maximum size linear. Okay, is that fine? Okay. What? What do you mean by did not understand? What do you mean what to do? These are set of rows, they are vectors, right? Because they are elements of A, right? So I can think of this like look at collection of maximum linearly independent rows in T provides you I in M, this is this, right? So if I look at my matrix A, right? This is my matrix A, right? T corresponds to some set of rows in this, right? B is a subset of that are linearly independent. If I have a matrix, I have a notion of linearly independent, right, over R, right, because I am talking only over R. So, this is just a set of linearly independent rows over R. There is nothing more to that. Okay. Okay. So, picture is gone. That is all that I know about pictures. That is all my imagination is. So, okay. So think of this as your constraint matrix A, okay, and let us assume that these are the rows of T. I mean, okay, these are rows of T, right, because if you do this permutation, it will not constrain anything. So this is like T, okay, and now let us believe that this is the rows of B, right. So B is contained inside T, T is contained inside set of column, T is contained inside 1 to n. Right? This is how the picture looks like. Now let us look at the corresponding. So I have a vector V, right. So let us look at this. I am going to call it BB. So look at the elements of B which corresponds to the rows B. So what is this? Elements of B that correspond to columns, correspond to rows in B, right. Okay. So what we know from this, if you notice, Bx is equal to Bb. This holds. Is that true? Because anyway they were holding with equality, right. So Bx is equal to Bb. B is this set of rows, that is a matrix, times x is equal to Bb. Okay. Okay. So a feasible solution x is called basic feasible solution if cardinality of B is n. Okay, that it satisfies, what does it mean? It satisfies n linearly independent constraints. That is it, or rows or column, whatever it is. Okay, basically n satisfies n linearly independent rows with equality. Is that fine? And what was n? N was number of variables, right? What was n? N was the number of variables. Okay. So basically geometrically what happens? If you think of geometrically, then this vector x is actually obtained by intersection of just n hyperplanes. Okay, but like my intuition is not, my geometry is not great. So if you have geometry, you can think of this way. Okay, but now what can we say about this? So look at this. So if you think of this way, what is A? A was a m cross n matrix because we have n. So what is the dimension of x? It is n cross 1, right? That is why you are getting B, which is m cross 1. Okay. Now there are n here, right? Okay. So, what we know from, because of this condition, what we know? Px equal to B, right. So, what is x? B, and this is unique because B has an inverse. Because why? Because it is a full, it is a full row rank. B has full row rank, right. You might think that it is, of course, this is not. What is the dimension of this? What is the dimension of B? B has a dimension n cross n, right. So, it is, so B is n cross n, right. It has a full rank. What does B implies B? Implies B is invertible, right. This is a unique solution. This is like just from the simple, okay. Is that fine? So, this is why I like this kind of service, because if I know this, then I don't have to care about other constraint. This constraint itself can give us the feasible x, right. So, what is the notion of basic feasible solution? A feasible solution such that the number, so the space of linear, what is the dimension of the space of tight inequality is same as the dimension of the program, which is n number of variables, okay. Such solutions are called basic feasible solution, okay. So, now why do we like them? So, let us write down other two properties of them, why they are interesting or nice, is because of the following reason. Again, I will not prove this. I think this weekend, this Saturday, we can have a class where someone else can give proofs to these facts. They are very simple proofs, okay. So, this is why. So, what is the fact 2? So, I use fact 1, right. So, here is the fact 2. Why do we care about basic feasible solution? If x is basic feasible solution, I am going to call it BFS, do not confuse with breadth first search. If you have seen simplex, it is all about going from one basic feasible solution to other basic feasible solution, right. Every time your cost increases, like the value it increases. So, this is why. So, this is basically what we are trying to do, is to give you an outline of a simplex algorithm without giving the proof, because we need it for lots of argument, okay. So, the whole one area of approximation algorithm called iterative rounding is based on basically an algorithmics of basic feasible solution, okay. Okay. So, why do we like? If x is a basic feasible solution, right, then there cannot exist, or maybe my English is not right, there cannot exist feasible solution, not even basic, x1 and x2 and parameter theta between 0 and 1, such that x equal to theta times x1, 1 minus theta times x2, okay. So, what I am trying to say, if x is a basic feasible solution, then you cannot write it in a non-trivial way as a linear combination of two feasible solutions. What does it mean? So, think, this is why these are called vertices. Why? Because they are not lying. So, therefore, this is, they are not lying on a line, they are here, right. Because if I could write it, then if my point is here, then I can write a linear combination of these two on the line, but it is not. So, basic feasible solutions are, these are like, they are what they call vertices of the polytope or whatever, right, some extreme points, okay. So, this is why we like them, right. So, if it is a basic feasible solution, then you cannot write a linear combination of these two. Like you cannot write a non-trivial linear combination of two feasible solutions. What about the converse? If I have a feasible solution which is not basic, then can I write it as a linear combination of something else? And the answer is yes. Okay. Okay. Again, so that's a fact 3. Not going to prove it. Okay. So this is your part of your assignment 2. Every such facts to give a proof, and they're easy. Or we can do it on Saturday if you can't do it, or some of you can do it yourself. Okay. If x is not a basic feasible solution, okay, then there exist two feasible solution x1 and x2 and a parameter theta between 0 and 1. Okay, it's 114. So, this is my last thing, such that x equal to theta times x1 plus 1 minus theta times x2, right. So, if you are not a basic feasible solution, then I can write as a linear combination, non-trivial linear combination of two feasible solutions, right. Okay. And what is most important thing, which is also like we can prove it's not very hard, okay. And this is the last fact that I need, and maybe I will prove if I have time. Okay. This is a fact 4. Okay. For any LP, okay, there exists an optimal solution x star which is basic feasible solution. That is it. Okay. So, they are the 4 facts. Okay. Either you can do it yourself, or I will write it down the proof and give it to you. It is not very hard. Okay. It is just by using some playing around with convexity. You can find it in any book, like for example, Papa Dimitriou's book on linear optimization, first chapter you will find anything. Okay. So, the only thing which I am going to use for my approximation algorithms, at least for next a week or 2, is that there exists an LP. For every LP, there exists an optimum solution which is basic feasible solution, and we can find it in polytype. Okay. Simplex finds a basic this thing. Okay. Yes. So, optimum lies on one of the corners. That is exactly what it says, completely correct. So, on the vertices, like there exists one, there could be an optimum solution which is not on the corner, but we will only care about that optimum solution which occurs on corner. Why we care about this? Because why it is interesting for linear programming? Because then we say, if you lie here, then there are a lot of constraints which are tight, right? And I can use those constraints for designing my approximation algorithm, because those constraints allow me to get better and better lower bound for my approximation algorithm. Okay, but that is just like a philosophy. I will show it. Yes, not all. Imagine I have a line. Any solution on this line will have the same cost.